We talked about a bunch of stuff, including the idea of Kw, and Kw is concentration of H plus times concentration of OH minus, and that equals 1 times 10 to the minus 14. That is something that you could use to calculate either the H plus concentration, which again is also can be the H3O plus concentration, which is really the acid part of the solution, and the OH minus is the base part of the solution. And you could calculate that. Really, it's the same calculation regardless of which one that you have. You're just going to basically take whatever one you're looking for, take 1 times 10 to the minus 14, which is the value of Kw, divided by really the concentration of the other guy. And if the H plus concentration is larger than the OH minus concentration, that means that your acid part is bigger than your base part. That solution should be acidic. If your H plus concentration is less than your OH minus, which means that the basic part of the solution is actually larger than the acid part of the solution, then it will be a basic solution. And if they equal each other, H plus equals the OH minus, then it is a neutral solution. We also talked about the pH scale. It goes from 0 to 7 to 14. Below 7 is acidic. Above 7 is basic. And 7 there on the nose is neutral. As you go from 7 back to 0, you're becoming more acidic. As you go from 7 to 14, you're becoming more basic in that particular case. We could calculate the pH like we talked about by taking pH is equal to negative log of the H plus concentration. Again, also you could do H3O plus in there as well. Remember, we talked about this formula, a couple other ones, depending on your calculator as to which way you should punch it in. Again, if you have a display calculator, you should punch it in exactly the way it's written, negative log, and then the H plus concentration. If you have a non-display calculator, then you really much need to go backwards. And again, start with the number, hit the log, and then hit the negative. Again, if you are not sure what type of calculator you got, just hit log, and if it does say log, it is a display calculator. If it says error, then it is a non-display calculator. We talked about at the end there, where we saw an example of a similar type of scale, which measures the OH minus concentration, and that is the POH, which is minus the log of the OH minus concentration. And the nice thing about that is if you take the pH plus the POH, it will equal 14. So for example, if you're given the OH minus, which I think is like the last example we did last time, you could actually calculate the POH if you want, subtract 14 from it, and that will get you to the pH. You could still also use Kw like we did as well, and you could use Kw to get the H plus concentration and then go into the pH. So they both will give you the same answer. Remember though, that as we talked about, you should always look at the pH scale in terms of if it's acidic, basic, or neutral, as the POH scale runs opposite. So if you have a low pH, you'll have a high POH and vice versa. So again, when you're asked that question, as we talked about last time, is it acidic, basic, or neutral? There is only one answer, yes, for a solution. So it should only be one of those three, not two or three of the three there. A couple other relationships that we saw at the end or talked about at the end, which was if you have the pH, you can directly get from that the H plus concentration, and that is equal to the inverse log of the negative pH. And again, on most people's calculator, when they hit the inverse log, a 10 and a caret usually pops up on the calculator, and you want to make sure it's negative pH. You also want to make sure, obviously, in this case here, that you are using your negative button, not the subtract button, otherwise you'll get an error. You also could do a similar calculation for POH. Directly from the POH, you can get the OH minus concentration by taking the same one, the inverse log of the negative POH. A reminder as well, with a non-display calculator, you also need to go backwards in this formula when you punch it in. You need to start with the number, make it negative, and then do the second log. Again, to do the inverse log on most people's calculators, top left second button or shift button that might be up there, and usually the log button that has like a 10 to the X That is usually how you do the inverse log if you need to punch it on your calculator. Those are the buttons that you want to look at and do. So this does give you, as we talked about last time, sort of a variety of ways that you can solve these problems depending on what's given to you. They all should get you to the same answer if you do them correctly, no matter which path that you choose. That's the important part of that, I suppose. It should get you the same answer. Any questions on any of that there? All right, let's see. Now, as we were talking about, the pH scale is based off of a log base of 10. So for every pH unit that goes up or down, the concentration changes by a power of 10, basically. So if you have an H plus concentration of 1 times 10 to minus 3, that's a pH of 3. 1 times 10 to minus 4 is a pH of 4. 1 times 10 to minus 5 is a pH of 5. Remember, as the H plus concentration increases, the pH decreases and vice versa. And again, that relationship that we talked about, as the H plus concentration goes up, the OH minus concentration goes down. So they do run opposites of each other, and obviously vice versa as well. One goes down, one goes up is the relationship there. Again, the lower the pH, the more acidic that solution is. Now, a couple of different ways that you can measure pH is use a pH meter. pH meter is basically an electrode. Basically measures voltages, and you calibrate it. And you calibrate it for like a pH of 4, a pH of 7, and a pH of 10. Then you stick it in your solution based on a calibration curve. It will give you your pH reading right there on the screen, basically. It really measures the amount of free H pluses that are floating around that solution. pH paper is another way that you could do it, kind of like you dip it in there, and then there's like a little scale. You kind of try to match it up to, what color matches as to what pH it is. Now, we also sometimes will use litmus paper, which does not measure pH, but it will tell you if a solution is acidic or basic. So if you have litmus paper and it turns red, that usually means that it's acidic. And if the litmus paper turns blue, it is basic. Again, will not tell you the pH or anything like that, but it will give you that information about whether or not the solution is acidic or basic. Here is our pH scale, and again, we see sodium hydroxide, which is a strong base, up there at 14. We have some hydrochloric acid, which is a strong acid, down there near 0, which is a pH of strong acid. Here we do have some acidic type things, vinegar, stomach acid, and so forth. We have some pure water here at 7. In reality, though, if you don't have pure water and you have water that's been sitting out a while, the pH will be in about that area, right about there. It'll pick up some CO2 from the air and create carbonic acid, increase the H plus concentration, actually lower the pH than what you might think. That's why sometimes people, if they want pure water, it's been out a while, they'll boil it. And when they boil it, they'll get rid of the CO2 and bring the pH back up closer to 7 and stuff like that in that type of situation. All right, so that's what we talked about a second ago. There are similar scales. Remember, the names do tell you what you need. So obviously POH means you need the OH minus concentration to calculate it. pH means you need the H plus concentration to calculate it. And again, if you add those together, it equals 14. So it does sort of give you some options. If you have if you want the pH, but have the POH, all you have to do is subtract 14 from the POH, and vice versa. If you have the pH and want the POH, you subtract the pH there from 14, and that will get you your pH or POH. So again, you may not have to use KW at all, but if you still want to use KW in certain situations, you still can. And again, it should get you to the same answer. All right, so let's try a couple more here. Good ones. All right, so for each of these, what's the pH, the POH, and is it acidic, basic, or neutral here? Okay, so let's take a look. So in the first one, we do have the H plus concentration, because we have the H plus concentration, that means we could go directly into our pH equation. And we could put it right in, and that'll get us minus the log of 3.6 times 10 to the minus 9. Again, if you have a display calculator, you want to hit your negative button, your log button, 3.6, your exponent button, your negative button, and 9, and hit equals. If you have a non-display calculator, you need to actually go 3.6 exponent button, negative button, 9, and then hit the log button, and then hit the negative button. Whichever way you do that there, you should end up with perhaps a pH that is 8.44 in this particular case. Now that I have the pH, I could very easily get the pOH from it by just subtracting 14. So the pOH in this case would be 14 minus the pH. Gives me 14 minus 8.44. Gonna get me 5.56 in terms of our pOH. Question on those two there. This would be acidic, basic, or neutral, this one. This one would be basic. Again, you want to look at the pH. pH is above 7. Again, don't look at both. Just look at the pH one. And again, just one answer for that one. All right, let's take a look at the second one there. And the second one there, we actually have the OH minus given to us, which means we could actually just start with the pOH because that is what is given to us. So we could go pOH in this case, negative log of the OH minus concentration, once again, because we are given the OH minus here. So when I do that, that's going to be negative log 9.2 times 10 to the minus 2 minus log 9.2 minus 2. Looks like a, go here, 1.04. At this point, I could easily get the pH by just subtracting. The pH here would then equal 14 minus the pOH. And that's going to give me 14 minus our 1.04. And that will get us a pH of like 1296 in this case. That means this one is going to be acidic, basic, or neutral. Also basic based off of the pH value over 7 of 12.96. Question on either of those there. Okay, so in this case, we're given the pH and just want the pOH. So we could just use the relationship that the pH plus the pOH is equal to 14. That would mean that the pOH here would equal 14 minus the pH. So we'll go 14 minus 5.67. And that is going to get us there 8.33. And in this case, the solution would be acidic, basic, or neutral. It would be acidic. Again, the pH here is below 7, right? So again, always look at that pH value. Question on that one there. All right, the pH is 3.14. What is the H plus concentration? Why we add a couple things. What's the OH minus concentration? What's the pOH? And is it acidic, basic, or neutral? All right, see what you come up with. Okay, so let's see how you're doing. In this case, since we're looking for a bunch of stuff, you do have a couple options. You can directly from the pH get the H plus concentration, so that you definitely could go direct from. Also, we have the pH, which means we could also get the pOH if we wanted to directly from that as well. So I'm going to start with the H plus concentration, and that is equal to the inverse log of the negative pH. Once again, when you pop that on your calculator, it should kind of look probably something like this on the screen-ish, maybe without the parentheses or maybe with the parentheses. And if you punch that in, you're going to end up with, I punch the right number in, that'll work. I will end up with an H plus concentration of 7.2 times 10 to the 1, 2, 3, 4, maybe -4. We do need molarity there as it's a concentration. Also, a reminder of sig figs, that's 2 decimal places, gives me 2 sig figs as I go to the concentration. So that is what we should look at. Now, again, if I want the pOH, I can get the pOH by taking 14 minus the pH. That would give me 14 minus our 3.14. So 14 minus 3.14. That gives me a 1086 on the pOH. And really at this point, since I just got the pOH, I do have actually 2 options to get to the OH minus. I could still use KW like we did before, where the OH minus is equal to 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4. And that would give me, again, making sure I use my exponent button here so that everything works correctly, hopefully. That'll give me like a 1.4 times 10 to the minus 11 molar. I also could, because I have the pOH, do the inverse log of the negative pOH, which again would be 10 and a caret negative 10.86, and that should get me there as well. So whichever way you want to do it should technically get you there and get you hopefully the right answer, you know. Now let's see, that takes care of most things here. This guy would be acidic, basic, or neutral. This one's going to be, this one is going to be acidic, right? Because our pH is 3.14, it's less than 7. Any questions on any of those there? Yeah. We got the 2 sig figs based off of the pH. So the pH had 2 decimal places. And because that has 2 decimal places, that means the concentration value should have 2 significant figures. So kind of going backwards. So remember, when we go from concentration to pH, we're going from sig figs to decimal places. So when you go backwards, you do the same thing. You go decimal places back to how many sig figs that would be. Yeah. Other questions? All right, let's try one more here. The pOH is 5.67. What is the OH minus in this case? So probably your best move would be obviously to use that to get to your OH minus concentration, which again is your inverse log of the negative pOH. Again, that should pop up at 10 and a caret, negative 5.67. Once again, if you're going to punch that in on your calculator, you have a display calculator. Again, the second or shift button, the log button, the negative button, and 5.67 and equals. If you have a non-display calculator, again, you would start with the number. We go 5.67. You would then hit your exponent button to make it negative, your second button, and your log button should get you there. And hopefully one of those got you to 2.1 times 10 to the minus 6 molar. Once again, 2 decimal places, 2 significant figures as we go over to the concentration. Question on that there. All right, question on calculate pH, pOH, OH minus, H plus. Any of those? All right. Then let's talk a little bit about what happens if we have or we want the pH of a strong acid. So up until this point, we've been given kind of generic like H plus, H3O plus, or OH minus. You could be given an actual formula of an acid or base. And if you are given a formula of an acid or base, especially in this class, you could probably safely assume it's going to be a strong acid, because a weak acid is a much longer calculation we don't do. But a reminder, just in terms of strong acids, these are our kind of 6 strong acids: hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, hydroiodic acid, and sulfuric acid. So those are like your 6 strong acids. By the way, base is the same deal. Strong bases, pretty much like your sodium hydroxide, your potassium hydroxide, your lithium hydroxide, calcium hydroxide, and so forth. So pretty much for our bases, um, lithium, sodium, potassium, calcium, strontium, barium, any of these guys kind of with OH in the formula are going to be strong bases in pretty much all cases. So when we look at something like HCl, which is a strong electrolyte and a strong acid, it is, as we talked about earlier, going to 100% break apart into ions, which means really in terms of the pH, it is the H plus concentration that's the most important. So if I know that this guy's concentration is 0.1 molar, as we talked about with concentrations, it is a 1-to-1 relationship between the whole thing and the H plus, which means that's going to be your H plus concentration. The good news is pretty much all of your strong acids, they're monoprotic, which means whatever their concentration is going to be pretty much the H plus concentration. So you don't have to worry too much about that. That means we could go into here and get our minus the log of 0.1 in this case, and that will get us our pH of 1.00, I think in this case. Question on that. So strong acids, if you're given a formula, pretty much that will most likely be your H plus concentration. Now, what happens if you're given a strong base? It works kind of the same way, except that when it breaks apart, you get a sodium ion and a hydroxide ion. So we do not have H plus, but we do have hydroxide. So if this was, for example, 0.1 molar, it would be a 1-to-1 relationship. The hydroxide would be 0.1 molar. That means that you could calculate not the pH, but the pOH in this case. And that would give you a pOH of 1. And then you could get the pH by taking 14 minus 1. I'll try without the calculator, 13, which is obviously basic in this particular case. So you could do the same thing for a strong base. The only difference is you'll have the hydroxide concentration, so you have to get the pOH first and then subtract 14 to get to the pH. I would say out of the acids or bases, it's probably the bases that you might have to adjust the concentration of the hydroxide, especially if it's in a group 2 sort of guide, because, for example, calcium hydroxide, when calcium hydroxide breaks apart, that is a calcium ion and 2 hydroxides, which means you do have to adjust the concentration there. So if this was 0.1 molar, this would be 2 times 0.1 molar, or 0.2 molar to get the proper hydroxide concentration. And again, I would say bases, probably on those group 2 bases are probably the only ones you have to worry too much about that if you even come across it. The other ones pretty much will be either the H plus or the hydroxide concentration. Any question on that there? Which means that it is going to 100% break apart in solution into H plus and perchlorate, which is this guy. And again, really, it is the H plus that is important for the pH. And again, as I was mentioning a second ago, pretty much because it's strong acid, it's a 1-to-1 relationship. And that would get you your concentration of your H plus. And now you're good to go right into your pH equation minus the log 0.025. Going to get you a pH of 1.60, looks like in this case, which is acidic, yeah, for sure. Question on that one there. Okay, so the next thing we're going to talk about then is, I think buffers is what we're going to talk about next here. So what is a buffer? A buffer is a solution that can resist changes in pH even when you add more acid or base to it. So a very common misconception people have about a buffer is it is a neutral solution, and a buffer does not necessarily have to be a neutral solution. It could be neutral. It could also be acidic. It could be basic. You can make a buffer at any pH you like. But what it means is whatever pH the buffer is at, it will be able to pretty much maintain that pH even if you decide to add some more acid or more base to it. And what is a buffer made out of? A buffer is made out of a combination of a weak acid and its conjugate base. Or sometimes it's referred to as the salt of its conjugate base. That just means it has like a spectator ion, like a sodium, a potassium, something like that hooked up in it. Or you can have a buffer made up of a weak base and its conjugate acid. Or again, it's sometimes referred to as the salt of its conjugate acid. A buffer cannot be made up of a strong acid or strong base. So a strong acid or a strong base, that is a no-no for buffers, yeah? So it cannot be in a buffer, yeah? And the reason for that is how a buffer works is it has to have both of those things in the solution to begin with. And because a weak acid or a weak base is a weak electrolyte, it will basically set up an equilibrium. And that's those guys with like the reversible arrows. So for example, if we took HF in solution, when HF breaks apart, because it's a weak acid, it will make H plus and F minus. Our everybody's favorite example buffers, which is acetic acid. When it's in solution, will break apart into H plus and some acetate here. So in solution, they have these reversible reactions. You could have like a buffer, for example, made out of that. You could have a buffer made out of those two combinations. What is the buffer in each of these cases? This guy here and this guy here is the buffer. And this guy here and this guy here, the acetic acid and acetate, is the buffer for that setup there. Again, it has an acid part and a base part. What is the difference between those two guys in boxes on each side? It is the Bronsted-Lowry definition, 1H plus difference. That is the only difference between them. So that kind of Bronsted-Lowry definition we talked about at the beginning of the semester, not semester, seemed like it, at the beginning of the chapter, is basically what a buffer has to be. The reason it's able to do that is it's a weak electrolyte, it's a reversible reaction. That's going to allow both of those things to stay in the solution at the same time. And this is also why you cannot make a buffer out of a strong acid and its conjugate base, because if you had something like HCl, it would break apart into H plus and Cl minus. Now, if you're trying to make a buffer out of these two, you're out of luck because when that goes for a swim, there's no more of that left, right? Because it all breaks apart. So you would only have a base part left in that buffer, the Cl minus, and that's not going to allow it to work correctly as a buffer. So that's why you cannot have a buffer that's made up of anything that's strong acid or a strong base. It has to be a weak acid or weak base, which allows it to basically set up that equilibrium in there and keep it in the solution. So how does a buffer work? Well, let's take a look at what happens when we add like an acid or a base to something that's not a buffer. Water is not a buffer. And if I added to my beaker here of water some hydrochloric acid and it went for a swim, it is going to 100%, as I just mentioned a second ago, break apart into ions. H plus and Cl minus. Which means in this solution, you'll have a bunch of H pluses and you have some Cl minuses. And what did you just do there? You just created a bunch of H plus really, really quickly, right? So we have a lot of H plus in that solution. And because that's going to cause the H plus concentration to go up, that will cause the pH to go down a lot. Yeah, so you're going to see a pretty big jump in the pH because you just added a bunch of H plus in there really quickly. H plus concentration shot way up. The pH, for example, might go from a pH of 7 down to like a pH of 2, a really big drop in the pH because of that sudden influx of all that H plus. That's what affects the pH, right? Is the amount of H plus or OH minus you have floating around in that solution, freely floating around in that solution. Now, if you took sodium hydroxide, which is a strong base, and put it into water, which is not a buffer, it also would break apart a lot into sodium ion and hydroxide ion. And again, in this case, if you dump that in there into water, you're going to make a bunch of sodium, which is not all that bad. But what is really bad is you're going to now make a bunch of OH minuses that are now free floating in there. And what's going to happen is kind of the same situation, except in this case, you just skyrocketed your hydroxide concentration. And because hydroxide and H plus are tied to each other, the hydroxide concentration goes up, the H plus concentration goes down, and now your pH is going to jump pretty high as well. You're going to start, for example, maybe at 7. If you found some neutral water, you add some sodium hydroxide to it, it might jump up to like a pH of 11 or 12 or something like that. A really big jump in pH. And that makes water not a buffer because it can't resist those sort of changes in pH. So how does a buffer handle it is, let's take a look at a buffer. I'm going to do HF, be different than acetic acid that everybody uses, and sodium fluoride. Also, I don't want to draw acetic acid a bunch. So we're going to do this, and this is going to be our buffer. And when we look at a buffer, this is hydrofluoric acid, which is our acid part of our buffer. And this is our base part of our buffer. And they are related to each other. This is a weak acid and its conjugate base. It's really the salt of its conjugate base because there's a sodium there. The sodium is doing nothing. It's just hanging out. It's actually the active part of the buffer is actually the F minus here. So from that NaF, it's really the F minus is really the active part of the buffer. So this F minus and this HF, the difference between them is 1H plus, just like in Bronsted-Lowry definition. So that is the two really buffer components. So what happens, for example, is when you put this into a beaker and you make this buffer solution, that HF is going to set up an equilibrium, arrows and all, that looks something like this in there. And again, that's going to keep in the solution the two things that you need for this buffer to work right. You're going to have the base part of the buffer, and you're going to have the acid part of the buffer hanging out in that solution together. So that's really important because now if I take, for example, my HCl, which is an acid, and I decide to drop my HCl in here, when I do that, will the HCl react with the acid part of the buffer or the base part of the buffer? They're called what type of reactions? Acid, base. So when you add that HCl to this buffer that contains an acid part and a base part, the acid will then go react with the base part of your buffer, which in this case is our sodium fluoride. It is going to do a classic, I don't know how classic it is, double displacement reaction that we talked about. We're going to switch some partners here. And you will always do this move right here, which is you will always make the other part of the buffer. So we are using some of the buffer, but we're going to make the other part. And then we're going to make sodium chloride. Sodium chloride is just a salt. It's actually a neutral salt, pH 7. Not a big deal. It's going to hang out. So when we look at this reaction that occurs when you dump this in here, we see that we actually make part of the buffer that was there originally. So that's not going to screw up the pH because that was there originally, right? So obviously that should keep it okay. We also made this salt here that's neutral. It's not going to mess up the pH. It's actually what we don't see here that we did see with water that is really important. What don't we see here on this side that we saw with the water part? When I added HCl to water, what did I produce? Produce a bunch of free H plus, right? And that is what makes the pH go crazy. In this case, no free H plus produced. And because no more free H plus was produced, the amount of H plus that was in there to begin with remains relatively constant. And if the H plus concentration stays relatively constant, so does the pH stay relatively constant. I say relatively constant because if you have like a pH meter and you're following it, the pH will go down, but it will not go down giantly. So, maybe you're at like, 4.95 and you add a little bit of acid, maybe it goes like 4.9 or something like that, nothing big. It won't go from like 4.9 all the way down to like 1. So you won't have that big jump like you will see in a non-buffer solution. You'll have a little bit, but it will stay relatively constant because we're not forming any more free H plus. So basically what's happening here, right, when we add this HCl, it's H plus and Cl minus, this H plus is able to go and find the fluoride and then make more of this guy, again bypassing the part where we're just adding H plus to the solution. And again, that keeps it relatively constant. Question on that there. So what happens in the other case if we were to add a base to this? So if we were to take this same buffer here, we'll draw it again maybe here. So we got our same buffer in there, our HF, our H plus, and our F minus, right? Pluses and all. There we go. And now what we want to do is put some sodium hydroxide in there. So when I put sodium hydroxide in there, that is a base, which means it should react with the acid part of my buffer. So it's going to go find the acid part of my buffer and do a acid base reaction, also a double displacement reaction. Going to switch some partners here maybe. We're going to get some water and we're going to get some sodium fluoride. Once again, just like we saw above, we actually make the other part of the buffer. This is why a buffer can withstand changes over a good period of time, because although you're using part of it, you're actually making some of the other part as it reacts. So as long as you don't go too much one way or the other, it'll be able to resist that change in pH for a good period of time. We also made some water here, which is not going to mess up the pH. Again, what we do not see here that we saw with the addition of sodium hydroxide to water, when we added the sodium hydroxide to water, we had a bunch of free OH minus. In this case, no free OH minus. And because there's no free OH minus formed, the concentration of OH minus stays relatively constant. And because H plus is tied to that, the H plus concentration is going to stay relatively constant. And guess what? So is your pH going to stay relatively constant as well. So in this case, what's going to happen is as that hydroxide comes in, it is going to react with this guy, make some water, and actually produce more of this guy at the end of it. So it's going to react there and produce more of that. Again, the idea here is how a buffer works is because it has an acid part to the buffer and a base part to the buffer in the solution together at pretty good concentrations when you make a buffer. When you add additional acid or additional base, it basically prevents the formation of free H plus that you normally would get when you put an acid in the solution, or free OH minus that you normally would get when you put a base in the solution. And because you're not adding any more additional H plus if you're adding acid, or OH minus if you're adding base, pretty much whatever your H plus concentration was originally will remain relatively constant. And that's how it's able to keep the pH constant-ish as to where it's at. Question on that there. Now, is there a limit to how all this works? There is. If you're going to make a buffer, for example, and you made a buffer and there's an acid part to the buffer and the base part to the buffer, when you add acid to this buffer, it's going to use up some of the base part and dramatically make more of your acid part and kind of use up some of your base part here. And if you add base to your buffer, it will react with the acid part and make more of the base part of your buffer. There is a limit to what's sometimes referred to as buffer capacity. let's just say, for example, I just keep adding acid. I don't stop. I just keep going. Or I added way too strong of an acid. It's going to eventually keep eating away at the acid part of your buffer until you have no more left. And then if you keep adding acid, now you're just dumping H plus in there, and you're going to then see a pretty big swing in the pH at that point. Same thing can happen on the right-hand side there. Actually, we're adding base on the left here. I guess we would have OH minus on this side. But on this side, same thing. We would eat up our base part from adding the acid and eventually add some H plus that would break through. That's why when you actually make a buffer correctly, you have to take into consideration the concentration of the acid or base you're adding to it and the concentration of your buffer itself, because you can make a really bad buffer, even though it technically is a buffer, that won't be able to resist the change of the acid or base coming in. So there is what's referred to as capacity. Any questions on a buffer, how it works? Okay. Now, the last thing we're going to talk about here is Le Chatelier's principle. And Le Chatelier's principle has to do with actually these reversible reactions. So it's this type of reaction here. Now, this type of reaction is a reversible reaction, has arrows heading in both directions. And basically, the idea here is there is a forward direction going from reactants to products. And there is a reverse direction going from products back to reactants. It's basically like a two-way street. So what will happen is eventually you'll make enough products that they will come together and go back the other way. And eventually this reaction will reach what is known as equilibrium. And equilibrium means that it is the rate of the forward direction will equal the rate of the reverse direction. Now, sometimes people, when they hear equilibrium, think it means you have the same amount on each side because it says kind of equal in it. And it doesn't really mean that. What it means is just as quick as it goes to the product side, those guys will recombine and go back the other way to the reactant side. So what that essentially means is when it reaches equilibrium, whatever everybody's concentration is at that point, they just maintain it pretty much. They lock themselves into whatever their concentrations are, or pressures, if it is pressures. They just kind of keep them, and they will keep those concentrations going on until you do something to screw it up. And you could screw up the concentrations or screw up the equilibrium. But the nice thing about these type of reactions is even if you mess it up, it will want to come back to equilibrium itself. It will force itself to come back to equilibrium. These type of reactions are also interesting because when you look at them in the beaker, you may look at it and go, it's done. Nothing else is happening. The reaction's over. It turned red or whatever it may be, right? But there's a lot of activity actually happening, even though it doesn't look like anything's happening, to going back and forth to keep it like red and keep the thing going back and forth. So that reaction, there's a lot of activity on the microscopic level, even though when you look at it in the big picture, it just looks like it's done. Nothing much is happening. There's a constant activity going back and forth, forwards and reverse reaction continuously happening. So when we have a system that's at equilibrium like this, we could add a stress to the system. And when we add a stress to the system, it will mess up the system. And basically, there's a few things that we could do to this system that will mess up the equilibrium. We could do something with concentration. We could do something with volume and pressure. We could do something with temperature. And we could add a catalyst. So what happens in this situation is, as I mentioned, we have somebody that's at equilibrium, which is basically that. Then you do some type of stress, it messes up the equilibrium, but it will try to fix itself. And the way it could fix itself is typically three options. It could shift to the right, which means you need more products, right? It could shift to the left, which means you need more reactants. Or you're going to make more reactants. Or there could actually be no change that occurs. Even though you did something to it, there's actually a chance that nothing will happen to it. So we're going to talk about each of these and sort of what happens in this case. So let's just say we'll start with concentration and see what happens. If we have a system in terms of concentration, there's basically two things that you could do. You can either add more, and when you add more concentration, it will shift away from the side you added it to. When we're talking about sides, by the way, we're talking about the actual equation, the balanced equation, left-hand side of the arrow or the right-hand side of the arrow, reactants or products, basically. The other thing you could do is remove something from the equilibrium. And when you remove it, it causes the shift towards the side you removed it from. So AA, add away, and when you remove something, it goes towards that side. So just a sort of example, let's say we had this little teeter-totter type thing here with some professional stick figures on it there. It's advanced stick figures, they have faces. So this guy on the left here is the reactant side of the reaction. This guy over here is the product side of the reaction. So what happens in this situation is we'll say he's at equilibrium right now. And let's just say somebody decided, hey, let's just hop on over here on the product side. When somebody hops on the product side, this is what's going to happen, I believe. Now, in order to fix this, obviously we messed up the equilibrium. To fix it, do I need more people on the right or more people on the left? And more people on the left, right? We added over here, we shift away from the side we added it to. We need to put more people over there, and it will once again come back to equilibrium position. In this case, back to equilibrium. Now, what happens if we have the same setup here? This is our reactants, this is our products. And let's say this guy decides he's just going to hop off. So when this guy hops off, we're going to end up in this situation. And to fix this, we need more people on the left or more people on the right? Yeah, we got to go towards the side we removed, right? I like to think of it as you removed on the left or the right, you made a hole. You got to go fill the hole, basically. You got to go towards the hole you made and fill it. And that will bring us back to equilibrium in this particular case. Any questions on that there? So let's just say I had this reaction here, and I added more B, and I added more D, and I removed C. For each of those, will it go to the left, will it go to the right, or will it have no change? So take a moment. So to this equilibrium, I did each of those things. Which way will it shift? Left, right, or no change? Add more B. So what we want to do is figure out where B is. B is over here on the left. When I add, it should go away from that side. So we add it to the left, it should cause the equilibrium to shift to the right. The reason that really happens is because when you add it to the left, you now have a lot more reactants and products. So they're going to find each other a lot quicker and it cause the reaction to go to the right-hand side because there's more reactants than products. I added more D. D's on the right-hand side. So I added to the right-hand side. It should shift away from the right-hand side, which means it should shift to the left in this case. Same reasoning, actually, when you add more D, add more products. So you now have more products and reactants. The reverse reaction is actually going to actually kick off and occur in that case. What happens if I remove C? C is on the product side. When I remove it, goes towards it, like there's a hole over there, right? I need to fill the hole, so it's going to go towards the side I removed it from. Any questions on that one there? All right, so let's then talk about volume and pressure. That's what I'm thinking. So volume and pressure are oftentimes related to each other, and they're related to each other by Boyle's law. So if you remember, the pressure goes up when the volume goes down. And basically here, when we have a smaller volume, it will shift to the side with the least number of gas molecules. When you have the pressure going down, you have the volume going up. When we go to a larger volume, we actually need more gas molecules. So it'll shift to the side with the most gas molecules. So personally, I think of these two related to volume. And if you have a small volume, you need to remember small, less gas molecules. If you have a larger volume, more gas molecules. So that's a good way to remember it based on the volume. It basically matches the volume, large volume, more gas molecules, small volume, less gas molecules. This depends on the equation you're looking at as to which side has more gas molecules. You basically add up the coefficients for everybody that has G's on each side of the arrow. And whichever one has more or less, then that's the deal. By the way, if you have equal number of gas molecules, it's a no change situation. There is no more or less side. So that is a possibility of how you get to like a no change. The next thing we're talking about is actually temperature. And temperature is the same as concentration, which means if we add more, it will shift away. And if we remove or lower the temperature, it will shift towards it. What makes it sort of which way it goes is the type of reaction that you have. If you have a exothermic reaction, that means heat and energy is given off. And by the way, that usually is shown perhaps sometimes with what is known as the delta H. So if you see that number, that value given to you and it's negative, it means it's exothermic. The number doesn't really matter, the negative sign actually. Pretty much if it's negative energy, that means it's exothermic. And what that means is we consider heat and energy to be a product. It's considered to be a product, heat or energy. So that means in an exothermic reaction, if you increase the temperature, it will shift to the left. And if you decrease the temperature, it will shift to the right in that case. Now, if you have an endothermic reaction, that means heat and energy is absorbed. And sometimes they show that with a delta H value that's positive or a positive value of energy. So it is thought of as being a reactant heat. A reactant. So same idea, if you increase an endothermic reaction's temperature, it will shift away to the right. And if you decrease the temperature of an endothermic reaction, it will go towards it and go to the left. So this one is dependent on whether or not it is exothermic or endothermic. And again, either it'll go to the left or the right, depending on which one it is. Question on that there. Lastly, a catalyst will actually cause no change. It'll just get you there quicker. A catalyst is not a reactant or product, is there to speed up the reaction. Other things that sometimes can cause no changes is like a noble gas because they're chemically inert. They won't react with things as well. So let's take a look here. Let's say we had 2A plus 3B goes to 6C in this case. And let's say that this reaction was exothermic. All right, so for each of these things, which way will it shift, to the left, to the right, or no change? Let's go with I add some A, I remove C, I increase the pressure, I decrease the temperature. So for each of those, which way will it shift? Let's take a look. So we're going to add some A. So A is over here on the reactant side. And whenever we add more concentration, it always goes AA, add away. So that should cause the equilibrium to shift to the right in this case. When we remove C, C is over here on the product side. So when we remove something, it's like making a hole over there, right? So we want to go towards the hole to fill it. So this would also cause the equilibrium to shift to the right towards the side we removed it from. Any questions on those two there? When we increase the pressure, again, I would think about it in terms of volume. So, and that's like really like Boyle's law relationship. So as the pressure goes up, the volume would go down. And since it's a small volume, if you will, we need less gas molecules. So counting up everybody with G's, that's a 2 and a 3. That is 5 gas molecules on this side. Over here, that's a G, and that is 6 gas molecules. So in this case, in this reaction, the least number of gas molecules is actually to the left, and it would shift to the left in this case. Any questions on that one there? Lastly here, if we decrease the temperature, we need to know exothermic or endothermic. It is exothermic, which means that heat is actually considered a product, sort of, which means if I put it on the product side and I decrease the temperature, that's like making a hole now on the product side, and it should go towards that hole to fill it, if you will, and it will shift to the right. Any questions on any of those there? All right, that wraps that up, I think. Your calculator and put it away. Not too far. You'll need it for exam 3. But no calculations now, all the way in, except for obviously exam 3 and the final with stuff we did before. But all these chapters, really no calculations going on. All right, so we're going to talk about organic chemistry. Organic chemistry, as pretty much any organic book will tell you, is the study of our friend carbon and carbon-like atoms, if you will. Basic organic type molecules are always connected this way. It is carbons to carbons, and usually there are hydrogens attached to those carbons. So this is essentially your basic sort of organic compound. What we will talk about is along the way, we'll change out some of those hydrogens for some other elements, and it will make different types of organic compounds. But basically, we have carbon and hydrogen at the core of most organic compounds. And let's talk a little bit about those things. Organic has to do with those carbons and hydrogens. A reminder in terms of polarity, carbon-carbon bond is nonpolar, neutral. Carbon-hydrogen bond also nonpolar. And that makes it, as you see here, not a great fan of water because water is polar. So water, which is polar, and these organic compounds, especially these guys here, that's just carbons and the carbons and hydrogens, they're not going to mix together because organic compounds, for the most part, will use dispersion forces as their intermolecular force, that really weak sort of force that holds molecules together. Water wants to use hydrogen bonding, which is relatively strong intermolecular force, and they can't really hang on to that interaction for a long period of time. So organic compound, like I said, is made up of carbon and hydrogen atoms. We again will swap out some of those hydrogens for things like oxygen, sulfur, nitrogen, phosphorus, some halogens in there. Because organic compounds are typically, for the most part, nonpolar or have regions that are nonpolar, they typically will have covalent bonds because it's carbon and carbon. Those are two nonmetals which will be sharing electrons. They typically will have very low melting points and boiling points. That is why a lot of organic compounds are volatile. They're held together by these really weak dispersion forces, and volatile means that essentially it will just pop into the gas phase super easy. Like you open the bottle and it's just going to pop. It was a liquid. You're going to kind of pop into the gas phase really, really easy. That's usually why they stick those things in a fume hood and stick you in a fume hood if you are doing a lot of organic sort of work in a real organic lab, because those things are also very flammable. So you wouldn't want a Bunsen burner lit while you're opening an organic compound that goes into the gas phase that's flammable and catches on fire. They are usually, again, not soluble in water because of that sort of interaction. They don't have a way to maintain that interaction with the polar water. And that's very, very different than inorganic compounds like ionic compounds. Those guys are held together by really strong intramolecular forces, the electrostatic attraction of opposites, positive charge, negative charge. And inorganic compounds are usually very soluble in water and they usually don't burn. You could heat the heck out of like a salt and it will just start to melt before, as we maybe talked about in the last chapter, go into the gas phase. Propane is an organic compound that's used as fuel. A lot of the first few organic compounds, methane, propane, butane, they're all gases, right? And again, that's because they're held together by these really weak forces. So here are some differences again between organic and inorganic. We typically have much higher melting points and boiling points in inorganic things like ionic compounds than we see in organic compounds. They're very, very low. And again, that solubility in water, very low in most cases for organic compounds and quite high for inorganic compounds. So we want to identify the characteristics that most typically is inorganic or organic. If it has a high melting point, it's probably inorganic. If it's not soluble in water, it's probably organic. It has a formula of all carbons and hydrogens, organic. Magnesium chloride, which is ionic and would be inorganic. It burns easy in air. That is organic. That's like the combustion reaction we talked about, right? When you go light your Bunsen burner, that's a combustion reaction. That's an organic compound, methane coming out, a little spark in air, and you got fire, right? Basically happening. Has covalent bonds, also organic, because organic's all about carbons, nitrogens, sulfurs, oxygens. That's all non-metal region where they're going to share electrons. Now, hydrocarbons are organic compounds that contain, pretty much like the name implies, only carbons and hydrogens. And one of the most important things that you should remember is our friend carbon has 4 valence electrons, and carbon should only make, one more time, only make 4 bonds ever. Yes? And I say that because people go crazy with carbon. Before you know it, it's got like 42 bonds to it. So it should never have more than 4 bonds. Also, a good friendly reminder, hydrogen should only have 2 electrons. Yes, so we have a lot of hydrogens floating around in the organic chapters. That again is what hydrogen should look like. Again, octet rule, 4 bonds, 8 electrons for carbon. Also, very rarely will you see carbon have dots. They're usually bonds. Yeah, so they usually make bonds. Very rarely, especially in organic guys, you'll see it have actually bonds. A saturated hydrocarbon means that that carbon has the maximum number of hydrogens it could have. It basically means it all has single bonds. Yeah, so there's all single bonds going on. So when we look at this carbon, because it's attached to this carbon, it has the maximum available hydrogen bonds that are left, and that is 3. Same thing with the guy on the right. It makes 3 hydrogen bonds here, and that gives it the maximum number of hydrogens. So a saturated hydrocarbon is an organic compound that basically has all single bonds, and that means it has the maximum number of hydrogens you could put on there. As we will talk about, pretty much if you're trying to draw something that's organic and you're out of things to put on there, hydrogen is what you put on there. And you put on to the carbons hydrogen until carbon has 4 bonds. So if I had like this guy and I'm drawing something, I'm like, what else should I put on there? Well, I'm just going to keep adding hydrogens to each of these guys until it has 4 bonds. And that's basically what you want to do when you're drawing these things, as we'll talk about. Now, carbon compounds like methane, there are some different formulas that we sometimes see in organic chemistry. This is a space field model there. That's the ball and stick model, like you are going to make a molecular model. That is the wedge and dashed sort of guy. The wedge coming out of the paper, dash going behind the paper is sort of 3D type of drawing. That is just the expanded structural formula. The expanded structural formula is pretty much like a Lewis structure where you draw out all the hydrogens. And this is the condensed formula where you don't draw out the hydrogens. You just kind of write it like you see there. So for example, you could have something like this. This is a condensed formula. Hydrogen is not drawn out, so that is the condensed formula. And if you wanted the expanded structural formula, you would draw it out kind of like a Lewis structure here. Looks something like this, where we draw out all of those hydrogens, basically. This is the expanded structural formula. By the way, there's also line structure that we sometimes use, which just are lines, basically, just like that. And each of those things basically represents a carbon. So although we don't write anything typically on a line structure, it's really minimalist. Everywhere I put a circle, that is a carbon. So there's a carbon at each of those spots. That's how many carbons then in that case? That is 5 carbon guy. Each of those carbons needs to have 4 bonds, which means although we don't draw it on this either, each of those carbons would have enough hydrogens to get it to 4 bonds. Guy at the end would have 3 hydrogens because that guy has 1 bond coming in, right? This guy has 2 bonds coming in, which means it would have technically 2 hydrogens. The guy next to it has 2 lines coming in, which means it has 2 bonds. Would need 2 hydrogens. Same thing here. And the guy at the end has only 1 line coming in, which means it would need technically 3 hydrogens there. So again, line structure is really minimalist there. We don't usually draw the hydrogens. You don't usually put little circles like I did there. Everywhere, though, I did put a circle, it implies that there's a carbon there. And the carbon there should have the appropriate number of hydrogens to get it to basically 4 bonds, basically. Question on that there. And that's sometimes called line structure there. Here is ethane. Again, the different sort of models there. I would say for us, these are probably the ones we'll use the most, and also line structure as well pops up as well. So in butane, predict the shape around each carbon. So let's talk a little bit about the shape here. This is just like we did when we did Lewis structures. If we look at this guy, which is a central atom, that is 1, 2, 3, 4 electron pairs, and 1, 2, 3, 4 bonds. That is your tetrahedral geometry. That is your bond angle of 109.5. Every single carbon here, because it is single bonded, will have that tetrahedral arrangement. Yeah, they all have 4 electron pairs and 4 bonds. That, by the way, is why when I draw the line structure for this, we get the what is sometimes referred to as the zigzag move there, because each one is tetrahedral moved in their geometry, so they kind of zigzag in terms of the way they go there. By the way, that would be the line structure for what we have going on right here. That again is 1 carbon, 2 carbons, 3 carbons, and 4 carbons happening right there. By the way, if we wanted to do the condensed formula here, we basically would write something like this. This would be CH3, which is basically this part. We would then go CH2, which is basically this part. We would then have another CH2, which is basically this part. And then we would have a CH3 at the end, which is this part, yeah? So that is, again, the condensed formula here. That obviously is, as I mentioned a second ago, the expanded formula where you basically just draw out the hydrogens basically. One's like a Lewis structure, and then obviously we have our line guy that has just lines basically. Any questions on that? Yeah. That's just the molecular formula? Yeah, so good question. So this is just the regular molecular formula. Yep. Yeah. So just like normal, it'd just be the kind of molecular formula for it. Other questions? So let's talk about the simplest organic guys you could have, which are alkanes. So what makes different types of organic compounds is there will be a part of that molecule that is special, and that will make it a certain class of organic compounds. And in the case of alkanes, really what is known as the functional group, and the functional group is the part of the organic molecule that makes it a certain type of organic molecule, is really the carbon-carbon single bond. So the carbon-carbon single bond is really the functional part of an alkane. They have all single bonds. Alkanes have a general form of CnH2n plus 2. What does that mean? It means, for example, if we take the simplest alkane you could have, it has one carbon. So N in this case would equal 1. 2 times 1 is 2 plus 2. It would have 4 hydrogens attached to it. And that is what is known as methane, your simplest organic guy you could have. Now, if I had 2 carbons, N would equal 2. 2 times 2 is 4 plus 2 is 6. And that would be ethane. If I had 3 carbons, 3 would be N. 3 times 2 is 6 plus 2 is 8 hydrogens. This is what is known as propane. These are all single bonded molecules. These are all carbons attached to carbons, and the hydrogens attached to those. So we saw ethane a second ago. I'm going to do propane over here. You basically would have carbon, 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 and again, our hydrogens would be attached like so. This would be our expanded structural formula. If I wanted to do my condensed formula, I have here at the end CH3, in the middle CH2, and CH3, right? And if I wanted to do my line structure, look just like that. 3 carbons, basically, yeah. By the way, these are all alkanes, which end in ANE. This name ends in ANE. This name ends in ANE. Not a coincidence. This name ends in ANE as well. That is how you name alkanes. You basically put ANE at the end of their name, and that is what makes it an alkane in terms of naming it. Question on that there. So we did those first few. Let's do the rest of them there. So we had our CnH2n plus 2. So as we saw there, 1 carbon, 4 hydrogen is methane. 2 carbons, 6 hydrogens is ethane, ANE. 3 carbons, as we just did on that previous page, 3 times 2 is 6, plus 2 more is 8, is propane. C4, 4 times 2 is 8, plus 2 more is 10. That is butane. C5, H12. 5 times 2 is 10, plus 2 is 12. At this point, we go prefix. Prefix for 5 is penta. So this is pentane, ANE. We go C6. 6 times 2 is 12, plus 2 more is 14. That is 6. Prefix for 6 is hexa. This is hexane. C7, 7 times 2 is 14, plus 2 more gives us 16 hydrogens. Hepta is the prefix for 7, so this is heptane. C8, H18, octa, octane, like you put in your car. C9, H20, no name. Could be making this up. C10, H22, decane. That's good for us. So these are the first 10 alkane names and formulas. Again, they are based off of this. You basically take the number of carbons, times it by 2, add 2 to them, and I'll tell you how many hydrogens you should have. The quicker you learn these first 10 names, the more enjoyable this part of the course will be. Everything that we learn and all the rest of the organic chapters, they will all come back to these 10 names. So everything will basically just come back to these 10 names. We'll do some slight changing to the name, but everything pretty much defaults back to these 10 names. So it's really important to know their names and how many carbons and hydrogens there are. And again, we'll always come back there. As you can see, these are all alkanes. They're all single bonded, no double bonds or anything like that in here. Everybody's single bonded. Everybody is attached carbon to carbons, hydrogens on the outside, basically, of those carbons attached there to get everybody to 4 bonds. Here is a table from your book. This is off by 1. The line structures are off by 1. So they go down. But here's our condensed for our first 10 and our molecular formula and our names. And again, everything does sort of fall back to these guys. So it's really important to sort of have those 10 sort of under control in terms of your names. As we talked about before, we could write our condensed structural formula by really just not drawing out our hydrogens is typically the way we do it. Also, if you do have a really long run, for example, of an organic compound, which you could have, and you just got a bunch of something like this, for example, it's just like CH2, 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 CH3, whatnot. But we got like 1, 2, 3, 4, 5, 6, 7, 8 of those. Sometimes people will kind of shorthand it even more, put a little parentheses and go, you got like 8 of these guys that just keep repeating. Yeah. And you want to make sure if you do come across something like that, there you realize how many carbons you got going on there, right? So we got like 10 or whatever I drew up there, and not just 3. So sometimes they'll kind of put in parentheses like a unit that just keeps repeating, and on the bottom is how many times it basically repeats. So this is like the shorthand to, something like that there. Question on that there. You can if you need to, if we have something really long. If it's not really long, I wouldn't do it on something that's kind of short. So usually just, if you got like, if you got this, usually you don't do that. So usually here you wouldn't just go, you usually wouldn't do that for something that's short. And so typically you wouldn't do it. Not that it's wrong or anything like that, but you typically wouldn't do it. You kind of reserve that for something really kind of long. So as we've been talking about, expanded, we show all the bonds. Condensed, we don't show the bonds to the hydrogen. This is our line structure. And again, we usually don't write anything in there. So it is really just a basic sort of formula. You could also have things coming off of it. By the way, if I have that line coming off of it, what's at the end of it? It is a carbon, actually, yeah. And it would also have 3 hydrogens coming off of it, right, at the end. So if you have something in a line structure and it's not a carbon, they will actually put it on there. So they'll write like what it is. So if you see just a lonely line there on the line structure, it's really not lonely. At the end of it, it's a carbon and it has 3 hydrogens. It's what's known as, we'll talk about, a methyl group, basically, that's hanging out there. But it is basically carbon. So in line structure, typically, if there's something at the end of the line, they'll actually write it if it's not a carbon. So they'll typically put that in there. For example, you could have something like this, and they'll put the OH to indicate that it's like an alcohol, for example, and they'll put something in there that you actually see it. So again, if you just see a line by itself, it actually is just a carbon at the end with the appropriate amount of hydrogens that should be there. All right. All right, so why don't you give this a go here? Given the following the reason I could just count the carbons is because I see all single bonds, which tells me it's an alkane, and it should have a CnH2n plus 2, which means N in this case is 5, and 5 times 2 is 10 plus 2. There should be 12 hydrogens hanging out, and you could count them if you want. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That would be my molecular formula in that case. Yeah. Questions on that one there. Condensed formula is pretty much the same thing as what we have, except we're not going to draw out the hydrogens. So we'll start on this side. This is basically a CH3. Right here, just going straight up, is a CH2. Coming here is another CH2. Coming here is another CH2. And here at the end is a CH3 in this case. And this would be our condensed formula, yeah? And obviously, if it has 5 carbons, all single bonded, 5 is penta. This is pentane, yeah? So this should be pentane in this case. Any questions on any of those there? All right. Why don't you write the condensed structural formula for ethane and heptane? And while you're at it, why don't you write the line structure for our. Okay, let's take a look. So first off, when we look at the name and we see ANE, that should tell us it's an alkane. And again, the general formula for alkanes, like we've been talking about, is this, if I could do it right there, 2. And ethane is actually 2 carbons, and that would be 2 times 2 is 4 plus 2 more is 6 hydrogens. That would be the molecular formula. The condensed formula would look something like this. And if you weren't sure, you could connect it up and equally distribute the hydrogens to get to your expanded structural formula. So this is the condensed formula. If you weren't sure, you could kind of draw almost like a Lewis structure and then just bring it down into here, right? So CH3, CH3 in this case. Any questions on that one there? Heptane, hepta is 7. So if you're not sure, I know that is 7 based on this formula. 7 times 2 is 14 plus 2 more is 16. And again, really the connection here is carbons to carbons. So a really easy way to do this is, if you want to do this, is to expand the picture so you can't see it. There we go. Is just start with the carbons, right? And a lot of times when you're drawing these things, just start with the carbons. So really what I'm going to do is just this. I'm just going to line up 7 carbons in a row. If I don't run out of room, 1, 2, 3, 4, 5. We'll go one more there, and we'll move my guy out of the way there. I think maybe a second here. Give me some room here. I'll get rid of that real quick. All right, so usually when you draw these things, this is really a good way to do it, which is draw up all your carbons, right? So we got 7 carbons, and here's all you have to remember. If there's no other element involved, which there is not in this case, everything else is hydrogen. And what did we say about carbon? It needs to have how many bonds? 4. So we're going to use hydrogen to get the 4. So when I look at this guy on the far right, it has 1 bond coming in, which means in order to get that carbon to 4 bonds, how many hydrogens does it need? 3, yeah? That is 3 plus 1 is 4. The carbon next to it has a bond here and a bond here, which is how many bonds? To get that guy to 4, he needs how many hydrogens to get to 4? He needs 2. Same thing here. 2 bonds needs 2 hydrogens. Same thing here. 2 bonds needs 2 hydrogens to get to 4. Same thing here. 2 bonds needs 2 hydrogens to get to 4. 2 longer bonds there needs 2 to get to 4. How about the guy at the end? He has 1 bond, which means he needs how many hydrogens? He needs 3. That is our however many hydrogens we counted there. 3, 5, 7, 9, 11, 13, 16 hydrogens. Yeah. That is really how you draw these organic guys. You draw up everything. You start with carbon, put everything else on, and at the very end, you just pop on enough hydrogens to give each of those carbons 4 bonds, and you'll have the right structure, basically. Yeah. Any questions on that there? So that is the condensed. Our line structure here would be, just keep going till you get 7, right? 1, 2, 3, 4, 5, 6, and 7. If I didn't mess it up, 1, 2, 3, 4, 5, 6, 7. There it is. Yes. There's nothing else there but carbons and hydrogens, and that would be your line structure, mountain range going on there. Yeah. Any questions on that one there? Now, cycloalkanes are actually alkanes where the end of the chain actually comes together. And there are a consequence of them coming together. And one thing that always happens in organic chemistry is essentially if you need to make a bond, you got to lose some hydrogens. And typically speaking, you lose 1 hydrogen from each of the carbons, because if you do not, let's just say, for example, we had propane, straight up propane here, looks like this, right? Looks like this. I'll kind of draw it like this. Now let's say we wanted to close this up into like a ring, which is basically a closed sort of system. What would be the problem if I just drew a line like that? How many bonds does this carbon now have? Has 5. Octet rule tells me that's way too many, right? So it can only have 4. And same thing on this side, right? This carbon now has 5 bonds. That is too many as well. So in order to make room for that bond to come in, we actually have to lose a hydrogen on each of those. So instead of 3 hydrogens on those guys, we will actually just end up with 2. We actually lose a hydrogen on each end. And now each of those carbons have 4 bonds and 8 electrons, and we're all happy here. And that means cycloalkanes are usually drawn in line structure. They're like their geometric shapes. That's like a triangle. And this has CnH2n, no +2 on these, because we lost those 2 hydrogens to close it up. So when you have to close this up into a ring structure, you lose those 2 hydrogens. So if you take a look at this, C3H3 times 2 is 6. This guy has 2 hydrogens. This guy has 2 hydrogens. And this guy has 2 hydrogens as well. And that gives you your C3H6. So cycloalkanes are actually named the same way as regular alkanes, except you put cyclo in front of it. Yeah. So this is propane in a ring structure is now cyclopropane. This is a cycloalkane. How many carbons does it have? It has 4. 1, 2, 3, and 4. It's in like a ring structure. It's closed, right? 4 carbons not in a ring structure is butane, right? And this would then become cyclobutane. Yeah. So you basically just put the cyclo part in it. It again has 2 less hydrogens than butane because it was needed to close the ring in, and you have to lose those hydrogens. Otherwise, it will have